Welcome to Genius Physics with Chamle Classroom, and welcome to the second chapter of Quantum Mechanics for Everyone video series. If you have not watched my previous video, I really encourage you to watch the first video because the fundamental equation, the fundamental classical equation that we simply turn into quantum stuff is there in my first video series. So I strongly encourage you to watch that video, the first episode, if you have not watched that episode yet. So classical wave equation. In my previous video, I derived the classical wave equation. Classical wave equation looks like this: delta squared y over delta squared y over delta x squared is equal to v squared times delta squared y over delta t squared. Basically, the v represents the velocity of the wave, and the y is the y displacement. For example, if you have a wave like this, a simple wave, imagine this is the x-axis and it's moving in the x-axis like that. So this y displacement at a certain point, so it depends on the x displacement as well as the time. That's pretty obvious. So now here, so we use classical wave equation to represent or to find the displacement at a certain point at a certain instant. Right. Put it aside for a moment. So then what I'm going to do is now, right, I'm going to find some solutions for this classical wave equation. Some legitimate solutions should be found out. So that's what my objective is. And even you guys have to work with me today. So if you have a piece of paper with you, that would really be helpful for you to take this down, because we have a lot of things to write down today. Right. Now, number one is I suggest a model. So I think that something like this could be a perfect solution for this particular equation. For example, let me take y, and y is the displacement. So for simplicity, I'm going to take it as y. Let me take it as y. And here, imagine it depends on two functions like this, or let me take even one function is fine when the other function is 0, but I'm going to take it as f x minus vt plus, let me take another function is there, which is g x plus vt. Right, now I have got two such functions. Number one is f x minus vt, and here we have g x plus vt. Right, so I don't know whether this is a solution yet, so you can't just out of nowhere, you can't just find solutions like that. So I'm going to find whether this is a solution, right? So what I'm going to do is, for simplicity, I'm going to take this as u. X minus vt is u and x plus vt is w, right? So I have now here y is equal to fu plus gw, and u and w are functions that depends on x and t. V is a constant. We already know what the v is, that is velocity, right? And right, if you're not familiar with these terms, so I think I should put it aside, because if you're not very familiar with these terms, it's my responsibility to introduce these terms to you. Number one is, there's something called wave number. In high school we mostly deal with wavelength and the frequency, but here we use them, but up to some extent in quantum mechanics we prefer to use wave number as well as the omega, in the sense angular velocity, rather than a frequency directly. So wave number k is represented, k is just introduced as 2 pi over lambda, which is wavelength. And on the other side we have frequency, or you can say omega, which is angular frequency, is equal to 2 pi f. Those are not new stuff. I mean, this is not a new equation at all, right? So even in one of my A-level video series, this is explained, so you can go through that video if you are interested. So this is not a big deal. So then I can, yeah, so what about this now? We know another one. So the velocity is equal to f lambda. So what if I go ahead and substitute these values? So f is now 2, yeah, so here I can say omega. No, let me rearrange a bit. So when I rearrange them, I will end up with here lambda is, in terms of k, I can write 2 pi over k, right? And here f in terms of omega is omega over 2 pi, right? So then I have v equals f lambda, right? So v is, right, so f is now omega over 2 pi times lambda is 2 pi over omega. So I can cancel out 2 pi to 2 pi, 2 pi over here, lambda is, sorry, my bad, k. So I will end up getting v is equal to omega over k, right? Useful, put it aside, but it will be very useful later, right? So remember this equation. So I need more space, guys. I'm sorry I had to erase this part, as I need more space. If you really want to, yeah, if you really want to take this down, so you can pause my video and take this down, right, in your book or somewhere else if you want. So I'm going to erase this part, as I can't keep it as it is, because I have to use this space for something more interesting. But this is very important. I will write it over here as it's very important, which is velocity is equal to omega over k. So that this same equation have been turned into this something written in omega and k. So let me erase this part. Right. Now we have got this nice equation now. So what I'm going to do is, now let me go ahead. So I'm going to get this side separately, and I'm going to get this side separately, and find whether this will match, or this will be a solution, whether this will be a solution for this equation, right? So I'm going to get this now, gamma squared, so sorry, gamma squared before that. So this is dabba y over dabba x. So dabba term, so those are partial derivatives, guys, in the sense here only it's a variable which depends on x and t, but here we assume that in this case t is a constant. So that is what partial derivatives represent. So I can just find this out, but here there's a problem. When I get the derivative, this is something, it is in u. So what I'm going to do is, I'm going to get that dabba fu, yes, but dabba u, right, and then here dabba u over dabba x. That's fine. Plus here dabba gw, right, over dabba here w, right? So and here dabba w over dabba t, right? Almost there now. But here something interesting I want to show you guys, dabba u over dabba x. Now here, when t is a constant, x is on the variable here, this one will be 1 and this one will also be 1. So I will end up with dabba y over dabba x is equal to dabba f u. I will put it aside for simplicity, guys. U is there, right? U is there, don't forget that. And dabba u plus, here we have dabba g over dabba w, right? It's not over yet. That's my first attempt, right? And then slightly move these, right? I have to start over here. So now we have double squared y is my next term, double x squared. I want to find it out now. So now here guys, when I get this relationship, same as on my previous case, so I take the same one, double squared f over double u squared, but in order to compensate this one, I have to take here double u over double x, plus same as my previous one, double g here over double w squared times here double u over, oh my bad, g, oh my bad, sorry, double w over double x. But again this is 1, and even here it is 1, right? Oh, here actually not t, my bad, that's x. Guys, here it's not t, it's x, right? So double w over double x, in case you are wondering what I did here. I made a tiny mistake, actually it's double w over double x here, right? So that's a deep explanation. So anyway, right, so this is now double w over double x, that's 1, right? So now here, let me go ahead and get something meaningful here. Double y squared over double x squared is now equal to double squared f over double u squared plus, right, here we have double squared g over double x squared, right? Put it aside, this is very useful. This is very useful, right? So that's the first part, in the sense this side of this equation, double squared y over double x squared, right? So that's not the whole story here. So I have to now just find what the other side is. So I keep it as it is now here. So that's my first found, so which is, I have to erase this one, guys. You can pause the video and take this down if you want. This is a long, a bit longer explanation. So but I have found out that double squared y over double x squared is equal to double squared f over double u squared plus double squared g over double x squared, right? That's it. That's the first sketch. Leave it as it is. So now I have to prove, I have to find something about this one, double squared y over double t squared. So just as my previous one, guys, it's still the y, the displacement relationship, and it's a function of xt, right? It's a function of xt, just as my previous case, is equal to f x minus vt plus g x plus vt. I think, right, that's our assumption. We think that this is the relevant function. We don't know it, and this is my now u, and this is my w. So y is again equal to fu plus gw, right? Okay, so now I'm going to get the second derivative of this one. So I have to get the derivative two times, right, in a row, and will eventually end up with double squared y over double t squared. Let's check, let's see. Now double y over double t, right, will be equal to what? So just as our previous one, I'm going to get the first derivative of this one, which is fu over double fu over double u times, you can't just write it alone, this is here now double u over double t, this time it's the derivation, I mean t's derivation, plus double gw over double w times double w over double t, right? Just as our previous one, check this out, guys. You will be able to see that double u over double t. Now x is a constant here. We treat x as a constant. So we'll end up with minus v here. So this is minus v, right? Here it is plus v. So we will end up with something like this. Double y over double t is equal to minus v times f or double f over w plus here we have v times dou by g over dou by w. Not over yet, but we are almost there now. Right, let me go ahead. I have to erase this part, though I don't like it. Right. Okay, so then let me erase this section. Right. I have to go ahead one more step, one more time. Dou bar squared y over dou bar t squared. Right. Let me get the second derivative of this one. Will be now equal to, we keep the minus v out of this one, out of the context. And here again, we have dou bar squared f over dou bar u squared times, again we have dou by u over dou by t, plus no, here plus v again dou bar squared g over dou by w squared times again dou by u over dou by t. Here not w over t, sorry. Okay, now here again, this is minus v, this is v. Carefully look at this. Now we will end up with dou bar squared y over dou bar t squared will be equal to, on this side, that's v minus v times minus v is v squared, and here dou bar squared f over dou by u squared plus here dou bar, here it's a common factor because even here we can get v squared, and the end of the day v times v is v squared. I take it out of the bracket. Let me save some steps. Right, so then here dou bar squared g over dou bar w squared. But can you remember here in this step we proved that this is dou bar squared y over dou bar x squared. So dou bar squared f over dou bar squared u plus dou bar squared g over dou bar x squared x is dou bar squared y over dou bar x squared itself. So I'm almost there now. What I can say is now, right, so I can prove that now. Here dou bar squared y over dou bar t squared is equal to v squared, right? This is exactly that, dou bar squared y over dou bar x squared. This is exactly our classical wave equation. So that is a perfect solution for that. So we have just proved that this is a perfect solution. This is a perfect solution for classical wave equation. So no matter what the wave is, so if you can write something like this, for example, let me write a few of these solutions, the relevant solutions like this. So the solutions are, now they will look like this, right? So you can have few solutions like this. Number one is, you can say y equals, right, how about this one, sine x minus vt. Oh, that's a good solution, right? With some modification, so I'm going to modify this later on. And you can write y equals e to the power I x minus vt. Oh, that's a perfect solution so far, doesn't matter. And y equals tan x minus 6, and you can add cos, right, another function like x plus vt. Even that's fine because there are two parts, but even if you end up with one of them, it's still fine, right? And here even if you write tan x minus vt, still it's fine. But here this is locally correct, but not globally, because locally in some regions tan exists, guys, but you already know that when this one turns into a product of pi over 2, it goes to infinity, so that you can't find a proper solution for that, right? Even someone says that ln x minus vt, that's a solution, yes, correct, but even this ln values can't get negative values. Therefore, that's correct, but only in the positive region, right? Only when x minus vt is greater than or equal to 0, you can find a solution for this one. So therefore, we conditionally in some other cases in physics we use these things, but here not in quantum mechanics. So we just cut this off from the scenario, from this context. We don't use these stuff, but this one and these exponential ones play a very important role, right? Especially the exponential term will play a very important role in quantum mechanics. So yeah, so I'm going to add some modifications to this one, right? So let me, simplest one is x minus vt, but we already know v is equal, we previously proved that it's omega over k, right? That's our proof. So when let me put it over here, then y is equal to sine here x minus omega over kt, so that I can just rearrange this a bit. So I'm not going to write it like this. In addition to that, right, even if I write the relationship like this, still my attempt is correct. Instead of this one, I write it like y is equal to k sine here k, and here yeah, x minus vt. Even that's fine because k is a constant, right? K is our constant, so that you can end up with y is equal to sine k here x minus v is omega over k t, so that when you put the k inside the bracket, so we will be end up with sine kx minus omega t, right? So this is a perfect solution. Even if you add this part, cos kx plus omega t, so this will be a perfect solution for this, right? So guys, in this context, so this is called a forward moving wave, and this is called a backward moving wave. So they meet each other. So in this context, waves can move in direction, so they will overlap. That's also fine.